of them inferred to exist in our own solar system. Only 2 are known to have come from our solar system from outside, discovered relatively recently, actually. Part of the mystery, because we should have been seeing these things for a while, maybe. Those of you who know the literature will know that interstellar objects maybe have been around longer than that. Certainly they've been reported in the literature for over a century in the form of meteors, that is smaller particles, millimeter size maybe, that burn up in our atmosphere. Though most of these are controversial. Not controversial because we don't think that they happen, but because the interstellar nature of these things depends crucially on precise measurement of their speed. And for a meteor, you only have a fraction of a second to do this while it's passing through the atmosphere. You really have to observe it from 2 different directions to get the full 3D positional and velocity information out of it. So it's a difficult problem in terms of meteors. For the 2 cases that I'm going to tell you about here, macroscopic objects, they've been observed over weeks or months by telescopes from different locations. Again, not our work, but they've been carefully measured, and there's really no issue that their speeds are high enough to make them interstellar. And I'll talk about this speed issue in more detail as we move along. What's really exciting about this is that they give us the potential to get a close-up look at material from other places in our galaxy, and even potentially to send a spacecraft to go and pick up a piece and bring it back to Earth. You can imagine, as an astronomer, if you're an astronomer, imagine getting a piece in your hot little hand or in the lab of your favorite astrophysical system that you've only been able to study remotely through a telescope up to that point. Piece of a protoplanetary disk, a supernova remnant, a white dwarf accretion disk. We don't know exactly where these things are coming from, though we have some guesses. But if these things are, if your favorite system is putting material out into the galaxy, that material is circulating around, and some of it is probably passing through our solar system. And that's what makes this kind of object so exciting. I should mention, maybe to head off a possible question here, is whether or not we might already have such interesting interstellar pieces in our own meteorite collections. So a meteorite, I'm not sure, there may be some undergraduates are in on the call. A meteorite is a rock which has passed through the atmosphere and survived that fiery event to drop rocks on the ground, which have been picked up. We certainly do have some meteorites in our collections whose origins are not precisely known, but it's probably, I wouldn't say that anybody's convinced that we have any interstellar meteorites in our collections right now, though it's certainly not impossible. So what are these interesting objects? Well, here's the first one. And I show this picture with some trepidation, but it made such a splash when it came out 3 years ago that it's hard not to show it. But this picture is not an image of the asteroid. It's an artist's conception. It's an artist's conception of Oumuamua. So Oumuamua is an asteroid, the first interstellar object discovered. It was actually discovered by a Canadian, Rob Warwick, who was and still is working at the Pan-STARRS telescope in Hawaii. Asteroids are named by their discoverer, and so Oumuamua is a Hawaiian term which refers to a messenger from afar. And the designation that you see here at the beginning, 1I, refers to the first interstellar object. So what's most striking about this picture to an expert is the extreme axis ratio of the object, which is about 10 to 1. And this is far more extreme than anything we see in our own solar system. It is really just part of the mystery. So this, again, is an artist's conception. It's not an actual picture of the asteroid. If I show you one of the best pictures we have of it as it passed near the Earth, we'd be looking at something like this. So it's the object in the circle here. For those of you, again, if there's any undergraduates watching this, the objects you see trailed here, these are stars which are trailing because the telescope is tracking the asteroid. So this is after the asteroid was discovered and we knew how it was moving, and we kept the telescope trained on it in order to get the best possible view of it. And what you see is a little dot here. And if you zoom in, of course, you do not see a 10 to 1 axis ratio. You just see some pixels. It is unresolved, as most asteroids are. So why was such a long axis ratio inferred? Well, in our own solar system, asteroids typically show brightness variations over a time scale of hours to days of about a magnitude or so. And the brightness of Oumuamua was also seen to vary over time. So here we have got, so this is time running along this axis here, and this is brightness along this axis. Brighter is at the top, lower is at the bottom. And the dots here all represent measurements from different telescopes. Again, not our work. And the dashed line here represents a shape model that is supposed to reproduce these observations and does pretty well. In our own solar system, asteroid brightness variations of this type are typically associated with shape variations. Now, they could be associated with a number of different things. Of course, you can imagine that the asteroid was white on one side and black on the other, and as it rotated, these albedo variations create brightness variations. But albedo seems to be a relatively small factor in our own solar system. What we typically see are brightness variations due to changing cross-section. So if an asteroid is not perfectly circular, then as it rotates, it will present different cross-sections to the sun and to us, and that combines to provide brightness variation. So here we just have a model shape of Oumuamua, and as it rotates, it reflects more sunlight back to us. Along here is sort of the integrated light reflected back to us, less there and then more there. And Oumuamua has an amplitude of its brightness variations of almost 5 magnitudes, which translates to a factor of about 100 in terms of flux. And so 100 in flux, when you're just reflecting light, means a factor of 100 in cross-section, which works out to be about a factor of 10 in axis ratio. So the picture here is a little bit uncertain. We don't know exactly what Oumuamua looks like, but this is in some ways our best guess. I would say that other authors looking at the same data, maybe with a bit more data taken a little bit later, have inferred that the axis ratio might not be quite as extreme, perhaps as high as low as 3:1. But even that exceeds anything seen in our own solar system, where the really reliable axis ratio measurements maybe top out a little bit above 2. There are some measurements which are higher than that, but with considerable uncertainty. So no matter how you slice it, Oumuamua is a very interesting object. Now, if instead we look at the here, maybe we don't have very much information. This is a spectrum, so we've got the wavelength running along here from blue at this end to red at this end. And what you're really looking at, there's really nothing of statistically significant here. You're just looking at a flat gray spectrum. What you're looking at is reflected sunlight. Maybe it angles up a little bit towards the red, so a bit of a reddish gray. This spectrum is very typical of the reflected sunlight spectra of ordinary asteroids in our own solar system. So there's nothing in the reflected light spectrum here to hint that Oumuamua is anything other than a very, very typical asteroid. Now, Borisov, on the other hand, is something quite different. It's not rocky, rather it's icy. And here we have a picture of it taken through the Hubble Space Telescope. What you're seeing is not actually what you're seeing is not actually the nucleus of the comet, but very deep inside this cloud, we presume at least that there's a mountain-sized chunk of ice. And that ice, under the action of sunlight, is vaporizing, sublimating, turning directly to vapor, and then being photolyzed by the solar ultraviolet to produce a variety of molecules which fluoresce to produce this beautiful cometary tail. And if I show you a couple of comets which are certainly from our own solar system, you can see that Borisov actually resembles them fairly significantly. I should mention that Borisov is a comet, and comets are named after their discoverer. So Gennady Borisov discovered this comet. That's why it's named after him. And 2I, of course, refers to the second interstellar object. That's as far as the count's gotten so far. But if I put Borisov next to some other solar system comets, you see similar structures. You see a dense coma where the icy nucleus is, fluorescing molecules being blown out by solar radiation pressure into a tail. And even though Borisov is maybe not exactly the same as these other ones, if I put 100 of these out on the table, you'd have a hard time picking out Borisov from the mix. It really, really looks like an ordinary comet. There are some molecular abundance differences, which have been flagged. Maybe nothing tremendously dramatic at this point, certainly interesting, but not immediately separable from ordinary solar system comets on the basis of its appearance. So the spectrum again, so again, we've got wavelength along here. Actually, maybe let's look at the top panel here first. Here, some of the features you see probably are statistically significant. The red line is a reflected solar spectrum, so much of the material being released from Borisov is molecules, but some is dust, silicates, sort of micron to millimeter size silicates, which reflect sunlight well, and so the spectrum is very much like a solar spectrum. But you do see occasionally emission lines like this, and so this lower panel here is really zoomed in on this emission line here. It's just a zoom in of that region of the spectrum. And you do see statistically significant emission lines. This is cyanogen, which is what gives the comet its beautiful blue color. So if we go back quickly to the picture on the previous, that blue color is very, very common in comets. It's associated with cyanogen and with our own comets from our own solar system. And so again, Borisov does not look particularly different in terms of its composition. So we're left with these two rather different objects. Even though Oumuamua was never resolved, the fact that it has such a asteroid-like spectrum, and the fact that it never displayed any cometary activity, despite passing rather close to the sun, much closer to the sun than Borisov did, in fact, this implies that at least to 0th order, it's a rocky asteroid-like body. Borisov, on the other hand, is behaving very much like an ordinary comet with a high ice content, water ice, other kinds of molecular ices. And so it looks very much like an ordinary comet. Why their compositions are so different is part of the mystery. We've got this new class of objects, and we've got two examples, and they're so different. If we only had one, we'd of course have a much easier time trying to explain this, right? But with two of them, that really makes things difficult. We've got to explain both of these in some way. And again, it's going to turn out that it's not so much the composition or the other obvious properties of these objects which make us believe that they're interstellar. It's really something else. It's their speeds. So I'm going to be showing some animations here, and I hope they're going to come across on Zoom all right. At the very end, I'm going to give a link to where you can find these online, full resolution, and some of them are on YouTube as well, so you'll be able to find them there. But we're going to be looking at some animations of the motion of these through our solar system. So there you can see a mock-up of our solar system. Here we've got Oumuamua coming towards the foreground here. And again, some of the information that you'll see here, though maybe it won't always be super clear through Zoom. I don't know how that's going to work, but you've got the distance from the sun in astronomical units, in this case 54.3 astronomical units, the AU being the distance between the Earth and the sun. And then its current speed, 27.0 kilometers per second in this case, and the local escape speed from the sun, 5.7 kilometers per second at this point. So this is actually going into the future. You can see the time up here. But what makes us really think that these things are coming from outside the solar system is this speed. So the speed here is well above the escape speed from the sun at all points. You'll also see in the background there some other spacecraft which we've launched, which are escaping our solar system for context. So I should emphasize that these trajectories were not observed in their entirety, and so we do not think that these are interstellar objects because we saw them far from the solar system and we watched them come in, and now we're watching them go out again. In fact, both of these were observed initially pretty close to the sun, where their reflected light made them fairly bright. The reason we think they're interstellar is simple first-year physics. So if you imagine the objects arriving with a certain amount of kinetic energy, they fall into the potential well of the sun. That potential gets converted into kinetic energy, and then as it swings around the sun, it leaves again, and that energy gets converted back to potential energy. As long as these objects don't have an encounter with a third body, like a planet, which we can verify through these kinds of simulations, it will leave with as much kinetic energy as it arrived with. And this conservation of energy allows us to determine as well that it was never bound to the sun. It arrived on an orbit on which it was initially already unbound. And that's why we think these things are interstellar rather than any of their other properties. And the physical argument is so simple to make that it's actually a fairly convincing one. There's not much that could happen that would prevent this from being correct. There are some, and I'll say something about that in a second. But here and now I want to show you running back in time. So now we've got the clock is running backwards. What we really want to do, of course, is trace these things back to where they came from. And here we see Oumuamua and Borisov retreating as the time runs backwards here, and they're leaving the solar system, if you will. Of course, at this point, they're really still within what we would call our solar system. But as the camera pulls back, we're going to pivot into the reference frame of the galaxy. That's the reference frame that we're really going to need to think of these things in going forward. So the checkered plane that you're seeing appear there is laid on the galactic plane. The other structures of the galaxy are not shown here in this view, but we've got the galactic plane, and the camera is pivoting so that you can see the orientation of our solar system with respect to the galaxy. So the galaxy is about 27 parsecs above the galactic plane, 25 to 27 parsecs. The galactic center is about 8,300 parsecs off in that direction. Again, that's not shown, but we're just giving you a bit of a view for what this looks like in order to get a feeling for the local neighborhood, if you will. We start in the reference frame of the solar system, the region of influence of the planets. We move out past the Kuiper Belt, out into the Oort cloud. We're still on the Oort cloud for certain at this particular location. But as we move back and as we want to trace these things back into the galaxy, we really have to start thinking of them in a different context. We need to think of them in the context of the galaxy. And so that's why the animation kind of brings you into this new reference frame so that we can start to think of them in this new context. This is the one we're going to have to think of them in terms of determining where their point of origin might be. So the galaxy is shown here. This is another artist's impression, but I don't feel so bad about showing an artist's impression here because we really can't get outside our galaxy and look at it from the outside, and so we have to reconstruct it from the inside. You can see it's a spiral galaxy with a beautiful spiral structure here. Again, not knowing exactly who's in the audience. If you're not familiar with spiral galaxies, they're collections of hundreds of billions of stars. Most of the light that you would see in this reconstruction is coming from stars. And if you look at it from the edge, you would see it's much flatter. So it has a kind of a pancake shape. And the galactic plane that I was showing you before, that checkered plane, sort of slices through the middle of the pancake. If you can imagine slicing your pancakes in the least convenient way possible, that's where the galactic plane lies, sort of on the middle, parallel to your plate, if you want to think of it that way. So for our purposes, we're mostly going to be interested in the regions of the galaxy closest to the sun. And so we're zooming in here, excuse me. So there you can see the sun and a region of about 1,000 parsecs around it. The sun is in the Orion arm, or here it's called the Orion spur. There does seem to be some debate as to exactly what the spiral arm structure is near the sun. That's not going to play a huge role in the arguments we're going to make here. But this is, again, just to paint a bit of a picture of the structures that we are going to be dealing with when we're talking about trying to trace these things back, at least within the local neighborhood. So in the spirit of painting a picture and trying to better understand our local neighborhood, here's another animation. In this case, time is frozen. Nothing is moving according to their appropriate velocities, if you will. I've just frozen everything, and the camera is pulling back to pan around and look at the local neighborhood. So you probably noticed that this is Alpha and Proxima Centauri there. Many of the other, hopefully most of the nearby stars are cataloged here. You see them in blue, in green and in white. The designations that you see there are actually from the Gaia Data Release 2 catalog. If we put the names of them there, then you would probably recognize most of these as local stars. But here we're just including the Gaia IDs. As we pull back, you can see that it looks like the stars end after about 25 parsecs, but actually what we've done here is we've just stopped indicating the stars. We haven't plotted any stars beyond 25 parsecs so that you can get a feel for sort of what kind of haystack we're dealing with here. There's about 1,400 stars in that region. And of course, that's only the region closest to the sun. So we'll play this again here. So the sun and the stars here are not shown to scale. They've been increased in size for visibility, but they're in the correct positions relative to the galaxy and relative to the sun. The checkered plane, again, is on the galactic plane. And the different regions that you see there are schematically shown schematically. These are different star-forming regions. These are the ones closest to our solar system. And the reason we put those in there is because asteroids and comets are expected to be ejected in large numbers during the planet formation process. And if you had to guess where asteroids and comets in the galaxy come from, you might guess that they came from forming planetary systems. And planets form at the same time as stars. And so if you want to look for sources of these kinds of objects, you might go to look at nearby star-forming regions. So we've got some of them there you'll probably recognize. There's Lupus star formation, Chameleon star formation region, and so forth. So you can see we've got a considerable set of objects to look through here if we want to try to determine where these things are coming from. So where could they be coming from? Well, I've already mentioned that they could have been ejected by the star-planet formation process. It's also been proposed that they could be ejected from binary stars. These are just some of the mechanisms which have been proposed in the literature. I bet you can think of other ones. Ejection from white dwarf systems, so the pollution or accretion disks around white dwarfs might eject material. And there are dusty, windy stars like asymptotic giant branch stars or YSOs, which could produce this kind of material, though that kind of material maybe is restricted to smaller dust sizes. And again, we don't know what the mechanism is, so these are just some of the possibilities. So now we're going to talk a little bit more about the work that Tim did. And to do that, I'm going to quickly introduce a concept which will be familiar to galactic astronomers, but maybe not to others. And that is the concept of disk heating. So it's long been known by galactic astronomers that young stars tend to be near the galactic plane and with a relatively small spread in speeds, moving on nearly circular orbits around the galaxy. Both of these increase with time as the stars scatter gravitationally off other objects in the galaxy, mostly massive objects like spiral arms and giant molecular clouds. And this process is called disk heating. It's not a thermal heating of the objects, which retain their normal temperature. Stars, of course, are hot. But this is a dynamical heating process where these initially fairly coherent orbits are perturbed onto more scattered ones. And this is actually something you've seen in the animations that I've already shown you. Both the two interstellars I've shown you already have been scattered by the sun. We saw Oumuamua come in along this trajectory and then be scattered gravitationally by the sun's gravity in this direction. Borisov came in like this and was scattered somewhat less in that direction. And this is the effect that we're talking about here. Young stars initially on very circular coplanar orbits get disturbed by these kinds of gravitational interactions. Ironically, stars like the sun contribute only relatively little to this overall. It's more massive objects that do most of this, but this is exactly analogous to the physical process that we're talking about here. So as a result, we can come up with a relationship between the age of stars and their velocity dispersion, at least as a population. So here, this figure, you can ignore this one. This is just one component of the velocity dispersion. So sigma here refers to the velocity dispersion. And this line here, also along here, you've got age, and along here, you've got velocity dispersion in kilometers per second. So older stars correspond to larger velocity dispersions, younger stars to smaller ones. And of course, you can draw a power line through that, as astronomers love to do. And if we know the speed of another object, like Oumuamua or Borisov, relative to the appropriate reference frame, in this case, the reference frame is the local standard of rest, we can add it to this figure and maybe learn something about its age. So if I plot Oumuamua on here, Borisov turns out to be quite fast, and so there's less to be said about it in this regard. It certainly does fit on this figure as well. But Oumuamua, again, is the more striking one. its velocity with respect to the local standard of rest is between 4 and 12 kilometers per second, which puts it down here on the graph. So there's 12 and 4 is down here somewhere. The uncertainty, this 4 to 12 kilometers per second range, doesn't come from any uncertainty in the velocity of Oumuamua, but we're actually from an uncertainty in the velocity of the local standard of rest. We know it to about 5% or so, but it is around 200 kilometers per second, and so 5% error gives you several kilometers per second of uncertainty. But no matter how you slice it, Oumuamua is moving quite slowly, unexpectedly slowly perhaps. And if we extend the age-velocity relationship out suitably, we find that Oumuamua lands somewhere at around 100 million years or so, so about half a galactic orbit. And so we might, from that, infer that Oumuamua is actually quite young. It has a low velocity with respect to the local standard of rest, which is characteristic more of young stars than old ones. And again, this gives it an age, notionally, naively, for sure, of only 100 million years, which is only about 1% of the age of the oldest stars in our galaxy. So that makes it unusual for yet another reason. Now, Oumuamua, of course, doesn't have a velocity dispersion. It only has a velocity. And so it's possible that it only has a low velocity by chance. So the velocities in the local solar neighborhood are drawn from a Maxwell-Boltzmann distribution that peaks around 30 kilometers per second. And there is, in fact, a 4% chance of drawing a speed less than 12 kilometers per second from such a distribution. So there's definitely a 1 in 25 chance that Oumuamua is older, but just happens to have a low speed because of this. But we're going to follow we're going to adopt the young Oumuamua hypothesis here and see where it leads us. So you might ask whether or not interstellar asteroids and comets should obey the age-velocity relationship for stars at all. And it's not entirely clear that they do. But if they are ejected by processes that occur primarily during the star-planet formation process, that is near a star's lifetime, near the beginning of a star's lifetime, and if they're ejected at low speed, we don't fully understand the processes by which these things are ejected, but it's always easier to throw a ball just over the top of a fence than 100 meters off over the top of a fence, right? So all of these processes tend to be more efficient at just getting things out on ejected orbits. So they're always more efficient at low speeds than high ones. And if this is the case, then it turns out that asteroids, comets, and stars should be scattered by the same processes subsequent to that. The influence of a GMC on an asteroid is the same as that on the star because of the vast mass difference. And so they should maybe follow the same age-velocity relationship, though that certainly remains to be verified. So if that's the case, again, we're going to focus on Oumuamua because its low speed means we don't have to track it as far back in time. Borisov, you could apply the same arguments here, but it has a much higher speed and so is presumably much older, which makes it much more difficult. So what we're doing here is we're now taking Oumuamua. In fact, we're taking 100 versions of Oumuamua in this cluster here. And what we're doing is we're applying 100 different Monte Carlo disk heating processes to them. So what we're doing is each one is being kicked individually in a manner suitable to reproduce disk heating as we understand it, and then integrated back in time. So the time was running backwards here. You can see the clock starts near the present day, and then it runs backwards, and you can see them diverge under this, this scattering process. The sun is also indicated there. The rest of the galaxy is present in terms of its galactic gravitational field, but the structures are not shown here to make things a little bit more clear. And as we go back in time to 100 million years when Oumuamua was presumably, again, making an assumption, ejected from its origin system, because Oumuamua must have been co-located with its origin system at the time it was ejected, that tells us that Oumuamua's origin system should have been in this region 100 million years ago, by virtue of the fact that they should have been coincidence in location at this time. So we have now narrowed down the region where Oumuamua's origin system should have been 100 million years ago. So that's interesting. We know maybe where it was 100 million years ago. Oh, in case this talk isn't technical enough for anyone, here's a couple of figures from the paper. So what you've got here, so here's the dispersion in position going back in time. So as that simulation runs forward, we're actually going backwards in time, and the dispersion increases. So this is the dispersion in position, or the standard deviation of the positions in parsecs as we go back in time. We use different models for the disk heating because we don't understand in detail exactly how that would be working, but you can see the different models produce similar results, and there's sort of a scatter of a few hundred parsecs in the positions at the end of that simulation, and this is the same thing for the velocity. You can ask me about that during the questions if you want to. So we've determined, maybe, modulo all our assumptions, that 100 million years ago, Oumuamua, and therefore its origin system, would have been in this region here. But what we'd really like to do is know where the origin system is right now. So if we now walk further out on our limb here, if we take this assumption that Oumuamua was ejected at low speed from its origin system at face value, then that means that the velocity vector of Oumuamua at this time is actually very close to the velocity vector of its origin system at this time. Oumuamua and its origin system would have been coincident in position and very nearly coincident in velocity when they were ejected. And so we can actually run this process forward in time. What we're going to do is we're actually going to assign the exact end position and velocity that Oumuamua had and now run them back in time. Now I've changed the color of the stars here to remind us that now we're looking at the origin systems for these objects. These are stars now, not Oumuamua. And they're running, now we're going forward in time. And they're undergoing the same disk heating process, but not with exactly the same random numbers. Of course, if they did, then they would just converge back to where they started. But we're now representing the uncertainty in this process by another set of Monte Carlo runs where we provide a similar set of kicks to the origin systems here as they go forward in time. So what's exciting about this, of course, is that now we can assess where the origin system would be at the current time, along with some understanding of the uncertainties which are inherent in this due to the disk heating process. And so through this, we are not yet at the point of being able to identify Oumuamua's origin system precisely, but we can circumscribe the region which probably contains it. And so even though Oumuamua and its origin system have both traveled halfway around the galaxy in the last 100 million years, they're traveling on paths which are very similar. They're nearby in space and with nearly the same velocities. So we can actually say with some confidence that Oumuamua, rather its origin system, is currently near the sun. And this is maybe not surprising. They both started at the same place with nearly the same velocity. It makes sense that in the current day, they would actually be nearby. But this means that in practice, oh, and here's another figure, again, for those who like to look at these. But here's the dispersion in the positions. So these values here are where Oumuamua ended in the previous simulation, and now we run forward in time. So these figures are a little bit tricky because we go backwards and forwards in time. They start to reconverge a little bit because, of course, the paths were diverging, and it takes a while for the disk heating process to randomize them and start them diverging again. But here is where we end. And so the scatter and the positions at the end of that last simulation here brings us back to the current time and tells us that 1 sigma, we probably know that position of Oumuamua's origin system within plus or minus 500 parsecs. Or if we ask what's 2 sigma here, 2 standard deviations, about 1 kiloparsec or so. So we have now reduced our haystack from all of this to a relatively small region closer to the sun. Of course, it's not actually circular. I've drawn it schematically circular here. It's actually a little bit more of an ellipsoid, but it means that Oumuamua's origin system is actually relatively close by. And that's exciting because it means that we could learn about it telescopically. We haven't pinpointed it yet here by this analysis, but if we can, that means it's relatively easy to study. And we can really exploit this synergy where studying Oumuamua will tell us about the origin system, and studying the origin system will tell us about Oumuamua. If we can make that link, we can learn a lot more than we can from either one individually, and that's really where these objects are going to become very, very exciting as levers to learn more about systems which may be far off in the galaxy. But of course, at this point, we really have not yet identified which strand of hay is the one that we're interested in, or I guess we're looking for a needle, aren't we? Sorry. We have not yet found our needle in the haystack. All we've done is maybe made the haystack a little bit smaller, but we've already seen that there's a lot of hay out there. And the back of the envelope calculation shows that if interstellar asteroids do not escape our galaxy and are not destroyed, then most of them will actually be too old to hope to trace back to their origin system this way. Disk heating will have erased the memory of their past, unless we're able to learn enough about where the giant molecular clouds and spiral arms were in the past. Then we actually may be able to reconstruct this. This was a suggestion I had when I gave this talk a little while ago, and that's really exciting, but we're not there yet. We're mostly interested in thinking about nearby sources which may be bright enough in terms of ejecting enough material that we could actually distinguish them from the background. And in this case, probably young star systems are our best bet, again, because the planet formation process is probably, I'm making a lot of assumptions here for sure, and you can grill me on this in the question time, but newly forming star systems may be the best places to look for these. So what we need to do here is not just use the positions of our objects of interest, but the positions and velocities of all the objects in our galaxy, ideally, to try to figure out where these things came from. Now, an exhaustive catalog of the positions and velocities of nearby stars does not exist. Well, I should say of all stars and all systems in the galaxy does not exist. But the Gaia catalog, currently at data release 2, is our best set so far. There are about 7 million stars with full position and velocity information, which is fantastic. But of course, there are of order 100 billion stars, sorry, in our galaxy. So we only really have a small fraction of these at this point. To these, Tim added some catalogs of nearby objects of perhaps particular interest. So catalog of suspected young nearby stars, catalog of moving groups by Gagne et al. There are others which you could imagine, including nearby disk systems and things like that. We're still continuing to improve and build this catalog so that we can include everything, everything that we can, but it's not easy to do. But these are the ones we've included so far. So I've been a little bit casual about exactly how this backtracking process happens. So I do want to say something a little bit more precise about that and spend one slide on this. So what we do is we use measurements of the in-solar system position and speed of these objects taken by other people at the telescope to numerically solve their equations of motion backwards through the planetary system and out into the galaxy. This is really just using Newton's laws, Newton's law of gravity. Not tremendously difficult to do, requires a little bit of care, but it's well understood. Out in the galaxy, the equations of motion are solved even further back in time together with our catalog of known nearby objects. So everything is numerically integrated backward in time, and everything is cloned. And that's similar to what I did earlier with Oumuamua. That is, we take several, maybe 100 instances of each object and give it slightly different positions and velocities in line with the measurement uncertainties. And then as we watch these things change over time, usually the dispersions grow over time, not because of disk heating, but just because they tend to spread, that gives us a way of measuring the effect of the uncertainty on how things are propagating backward in time. We want to be very aware of that. It turns out that the uncertainties in Oumuamua and Borisov are actually negligible in this context. Most of the error comes from the uncertainty in the positions and velocities of the stars, but we account for it all. The galaxy is modeled as a time-independent three-component potential, so we do not include the effects of individual stars at this time. We do want to include those, though you can show that they're probably a relatively minor component in the grand scheme of things. And then we look for close passages between catalog objects and our objects of interest to see if any of these could correspond to an ejection event. So what I'm going to show you here is the results of some of these simulations. So what you're looking at here is actually the last 100,000 years of the simulation of Oumuamua within the context of our galaxy. There's Oumuamua and there's our sun. The checkered plane, again, is the galactic plane. And what you're looking at there, each of those little spheres is a star from the Gaia DR2 catalog. The colors are representative of the effective temperatures. Red stars are cool stars, yellow stars are hotter stars, and so forth. And all of the motions here are an accurate representation of their motion over the last few hundred thousand years or so. You can see the clock in the upper right. None of these are actually thought to be the systems which ejected Oumuamua. The blue lines that you're seeing there are lines which connect the stars to Oumuamua when they pass within 5 parsecs of each other. So even though this is a fully 3-dimensional simulation, it's sometimes hard to tell which ones are actually passing nearby. And so those blue lines are there to call out any approach within 5 parsecs. Though 5 parsecs is probably too far to represent an actual ejection event. Probably these would have to get within the size of the spheres that are indicated there. Each of the spheres is actually about the size of the Oort cloud of the star. And so they're much larger than they are in reality, of course, here in this display. But it gives you an idea of the final approach of Oumuamua to our sun. I'll show you the same thing here for Borisov. It looks rather similar. You can see the sun over here in this case. If I showed you the full animation, it would actually take about as long as a full-length feature movie. It takes about 2 hours to go through the whole thing. And again, none of these events are the ones which are likely ejection events, but they give you an idea of the scope of the problem here. They're just there to sort of illustrate how active, how dynamic the local neighborhood is. Some of that gives you a feeling for some of the motions here. We haven't even indicated the uncertainties in the motion here. That makes things even a little bit more complicated. But the local solar neighborhood is actually one where things are moving around at a variety of different speeds, and this makes things difficult to piece together sometimes. So what are the results? Can we trace Oumuamua in particular back to its origin system? And the answer is that at the moment we have not done so unequivocally, though we have a couple of good candidates that we're hoping to refine. The best candidate region is the Carina-Colombo moving group, which is a set of young stars which has left its birth cluster but still moving together. Oumuamua encountered it at relatively low speed, about 30 million years ago, and this is also the estimated age of the cluster. So the cluster is estimated to be 30 million years old, and this feeds into our thought that perhaps these are produced by the planet formation process. If that's the case, then 30 million years ago is when this cluster was ejecting the most material. And so we've got coincidence in position, coincidence in velocity, and coincidence in time that are leading us to link these together, but it's very difficult to do unequivocally. Our second best candidate is probably the Lupus star-forming region, where Oumuamua had a similar encounter in terms of distance and speed about 18 million years ago. But the Lupus star-forming region has an estimated age of only about 3 million years, which might make it a little bit less of a candidate. But if you look in the literature, you'll see there have been suggestions of older bursts of star formation as well. So maybe the Lupus star-forming region is actually older than most best estimates put it at, and that means maybe it is a potential source of these kinds of objects. Borisov, we've done a similar analysis on, but because it's moving so fast, it's harder to trace, and we don't find any really strong candidates for possible local origin systems. So in conclusion, these kinds of objects really are multi-messenger astronomy in some sense. If you could actually get one of these things or a bit of one of these things and bring it to the lab, think of how much you could learn about systems which otherwise we can only study remotely through the telescope. Fantastic as the telescope is, it doesn't tell us everything. But to really leverage that, to really understand what we're seeing in the lab, we really need to know where these things are coming from. We need to know their geological context, if you will. Oumuamua is really unusual in a lot of aspects, and because of its lower speed in particular, it may be quite young, unusually young. Even though it and its origin system have traveled halfway around the galaxy since it's been ejected, maybe, you can quiz me on that, Oumuamua's origin system could actually be right nearby and a potential rich source of information about it. Only we can figure out which one it is, which we haven't quite done yet. So we're certainly beginning to piece together the past history of these really, really interesting objects, but there's still a lot of work to be done. So thank you very much for your attention. If anyone did have trouble seeing the Zoom animations, you can find them at this link here, or you can find them as well. Most of them are up on YouTube as well. So if you do a search on the web or on YouTube, you should be able to find them there. So I'll leave it at that.
Thank you, Paul. That's good. Very interesting. So amazed that we have interstellar visitors, but that's good. Okay, so people have questions. I have a few in the chat window, but I'll go through those. But could you raise your hand when you have a question? So one from Terry Bridges, what are the chances that Oumuamua could have been scattered by another star before entering our solar system?
That's a great question. It's certainly not impossible, but if you look at the expected time between encounters, so if you ask how long should it have been since Oumuamua had an encounter with a star as close as the one that it had with the sun, the answer is more than a Hubble time. So these things encounter stars this closely only very, very rarely. But it's hard to say unequivocally that it couldn't have happened, but statistically it's extremely unlikely.
Okay. So I have two kind of related. One is about an article this week that claimed Oumuamua is a chunk of frozen hydrogen. And then a question from some John McDonald. That comment earlier was from John Hutchings. And then John McDonald says, how would the hypothesis of Seligman and Laughlin that Oumuamua is a hydrogen ice body affect your conclusions about origin?
Yeah, that's really interesting. There have been some really interesting thoughts on what this thing might be. It's got so many weird things going on. It's hard to exclude anything in particular. I study asteroids, and so it's very easy for me to think of it as an asteroid, but that's probably a very, very dangerous thought, and one which I try to avoid, an assumption which I try to avoid making. I don't know enough about the properties of frozen hydrogen and some of the other proposals which have been put forward to say anything unequivocal about whether or not it could have survived or the properties like that. But there are lots of interesting ideas that I think cannot be excluded at this point. Because of its strange shape, it's sometimes been described as a shard of a planet. You can imagine a rocky planet with a glass-like composition which could explode into shards, which might have these long axis ratios. People have tried a lot of different models. I'm not familiar with this particular paper about hydrogen ice, so I can't comment on it definitively, but I think all options are open at this point.
Okay. Question from Magdalene Normandou. I don't understand how reversing your model gives you information about where the formation system should be now. It feels like going around in circles. So I must be missing something.
Yeah, well, we certainly, I mean, we're not quite going around in circles. What we do is we try to extrapolate backwards with our best understanding of the uncertainties, and then we go forward under the same scattering processes, and you know, the error bars get bigger. We're changing the direction of the sign on the time step, but so, I mean, it's not completely circular, but we are applying the same process to Oumuamua going backwards in time that we then apply to its origin system moving forwards in time. So there's certainly some, I mean, we sort of come back along our tracks to a certain extent, but we apply a completely independent, random scattering model to the system to try to capture this. I'm not sure if I have really answered the question, but I'm happy to take another crack at it as well.
Okay. Doug Johnstone has his hand up. Go ahead, Doug, unmute yourself.
Sure. People must ask you this all the time. Life, why not a spaceship? So can we, once we start playing these games, is your probability low enough that you start to think, I wonder why this actually arrived here?
Yeah, that's a tough one, right? These things are so strange. It's hard to, we tend to naturally fall into maybe a well-worn thoughts that these things are not, these are just naturally occurring objects and blah, blah, blah. They've got to be, if you look at the number of asteroids and comets which have probably been ejected into the galaxy over, the lifetime of our galaxy, the number is stupendously high. And so it's not surprising that we would eventually see some of them. But the properties of Oumuamua are so strange. People have proposed that it could be a spacecraft of some kind. There have been some measurements which show it may have accelerated moving out of the solar system. I'm not convinced, but I've talked to other people who are very good, very, very accomplished asteroid researchers who see the data look very good. I don't know what to tell you, but again,
you're doing everything right? We should be looking at all of these and the like, but it's just fascinating that the first thing we find is so weird. All of this other stuff that's the part, or maybe we're missing something really fundamental at the moment. But excellent, thanks.
Yeah. No, if anybody has more ideas, I'm happy to hear them, because I think we want to avoid being too quickly shuttered into our assumptions, for sure.
Question from Dave Balaam. Can you explain the non-gravitational acceleration when outgoing?
Yeah, okay. So so I alluded to this. Dave will know about this for sure. I cannot explain it. What Dave is referring to is that as Oumuamua was leaving the solar system, of course, it was heavily observed, and there were some indications that it was accelerating, not fast maybe, but noticeably on its way out of the solar system. Some people have tried to ascribe this to cometary activity. You can imagine that if there was ice on Oumuamua and it was escaping, it could create a jet-like effect. But of course, Oumuamua showed almost essentially no cometary activity, so it's hard to imagine. It is a bit of a difficult measurement to make, in my understanding. So, Dave, you know more about this than I do for sure. But if you're looking at something moving directly away from you, isn't it hard to tell if it's accelerating or not? Maybe you can comment on this more knowledgeably than I can. But I don't have an explanation for it. I don't know if it actually happened, and if it did, what might be the cause.
Okay, next question is from Jean Malone. Given its faintness, I don't suppose anyone was able to get a sufficiently resolved spectrum showing hydrogen emission lines in Oumuamua.
As far as I'm aware, no. I haven't seen any in the literature. Maybe there are some out there which haven't been published, but I'm not aware of any detection of hydrogen lines in any band from Oumuamua.
I have a question. How many of these can we expect in the future? How frequently might these objects be visiting us?
Yeah, that's a really interesting question. Theorists were very happy to say that this happened hardly at all about 10 years ago. And now all of a sudden people are thinking that maybe this should have been happening more often. The short answer is that we don't really know. And there certainly are some questions. I've talked to some people at some of the asteroid surveys as to whether or not they're looking in the right way to find these things. Because of course they're mostly interested in finding real asteroids, and real asteroids are mostly bound to the sun. And so some of their protocols are not perhaps optimized to find these interstellar objects. Though I think that now that these things have been discovered, they're improving those. I think that the test will really come when the Rubin Observatory comes online and it really starts to survey the whole sky at high cadence. That's when we'll really start to know how many of these things are out there. At this point, it's hard to say. We should have been seeing these things for maybe the last 20 or 30 years, but we've only seen them in the last few. That's sort of part of the equation. it's a tough problem. These things are really a puzzle on a lot of fronts.
Okay, well, thank you. If there's no further questions, I want to thank Paul again for a very excellent talk, very fascinating subject. And so let's all put our thumbs up or clap or something there. And yes, let's see the screen filled with yellow markers.
Yeah, thank you very much. Very, very happy to be here.
Good. I'll just let people know that next week speaker is Doug Johnstone from Hertzberg, who will be, the title of his talk is What the Submillimeter Variability of Embedded Protostars Tell Us About Accretion, Past, Present, and Future. So enjoy your week, everybody. Stay safe, and I look forward to seeing you all next week.